Hey, this is Mr. Leach with Simpson Math, and today I'm going to be talking about the limit. I'm going to be using an applet available on this website. You can copy it down here, or the link should be in the description below. When you go to this link, you should see the applet on the left of your screen. The first thing I want us to do is to graph f of x equals x squared. So on the bottom left of the applet, delete out the function that you see there and type in x caret squared. In order to get the caret, hold down the shift and then hit the 6 button, and so then that's x squared, and hit enter, and it should graph it for us. So I want us to find the limit as x approaches 1. Well, to do that, let's play around with this applet a little bit. Move your mouse to the x-axis and see that you can click on that point labeled C. I'm just clicking and dragging. I can drag this higher, I can drag it lower. Let's drag it so that way that C is on 1. It should probably just snap a little bit to that. And we can see that the value C, if I plug in C into the function, it does give me 1. If I plug in 1 into the function, we see that it touches the function here, and so that value is 1. So I can adjust this delta, which is this red area. I'll talk a little bit more about the details of this in just a second. But I can make this a little bit wider. I can increase delta, which makes that red area bigger. I can make it smaller, which makes that red area smaller. And it also moves that green area as well. So I'm going to put my delta to 0.3. And we can see that the highest point of this red zone corresponds with the highest point on this blue part of the graph, which is the highest point on that green. And the lowest point does the same thing. So we can see that this green part are the y values. So the idea of the limit is as x approaches 1, that's from the left side and the right side, it's going to be getting closer and closer and closer to something. So if I make this smaller and smaller and smaller, we see that it does get closer and closer and closer to 1. Let's do 0.5. So I'm going to move my bar over to 0.5, and we can see that if I have a really big delta, the bottom of the green interval is not the end of the graph, it's actually the minimum. And so if I can make this be smaller and smaller and smaller, again, it's getting closer and closer to the graph, and we can see that 0.5 does go to 0.25. Now let's take a look at the function that we saw a second ago when we first loaded the applet. So just hit refresh. Let's talk about delta, and let's reference the definition of the limit. So as you can see, this function, it has a floor function, it has some signs, it has a bunch of stuff in it. The function itself is irrelevant, it's just unique. Let's take a look at the definition of the limit. So it says, let a function with a domain D that maps onto the real number R, so this is my range and this is my domain. So the domain is any set D, but that maps onto the real number set for the range, be a function defined on the subset. So D is a subset of the real number set. So that means that my domain is a part of the real number set. Let C be a limit point. So this is our C right here. Let C be a limit point of D. So C is in our domain. That's why C is on our x-axis. The domain is the interval of our x values. And then let L be a real number. Then the function f has a limit L at C. So C does give me some sort of limit, and so that limit is an output. So that limit's a y value. It is defined to mean for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in D. So we have this epsilon and delta. So delta is on the x-axis. That's this bar that we've been adjusting. So if delta here is, let's put it to an easy number, about 0.5. Let's move C here to 1.5. We can see that this goes up 0.5 and it goes down 0.5. So this is sort of kind of like a radius idea. So what this means here is that for C, I have a delta. So my delta is sending me all the way up to 2 and down to 1. There, I can take any x, I can take some x that is between these two. So I can pick 1.75, which would give me a distance that's smaller than my delta. So then that means I must be able to shrink that in a little bit. Okay, so if I shrink my delta down to 0.25, well, I can pick an x that's smaller than that. And so I can make my delta even smaller than that. And then I can pick an x that's smaller than that, and I can make my x smaller, and I can make my delta smaller. So we can do this over and over and over, making delta smaller and smaller and smaller, and that corresponds to this inequality, the function f of x minus L is less than epsilon. So when my delta is up here at 0.5, I could, if my x that I picked was 1.75, that is smaller, that is between C and the point above delta, well, that also means that there's some f of x. There's some f of x over in this green space that, if I subtract that from the limit point, that is smaller than some epsilon, where epsilon is some total distance of this green space. And so as I make delta smaller, epsilon should be getting smaller and smaller and smaller as well. So that's the definition of the limit. So what's the relationship between the red segment on the x-axis and the green segment on the y-axis? We sort of kind of talked about that. It seems casually that as I make delta bigger, green seems to be getting bigger. As I make delta smaller, green seems to be getting smaller. But a few things of note is that it's not necessarily the largest point on the red interval that produces the highest point on the green. As we can see here, the highest point on the green is because of this maximum point right here, not the highest point on the red. It's the maximum range within this interval on the domain. As delta shrinks to 0, does the green area always get smaller? So it's important to note the word always. So let's sort of watch this. So let's make delta as big as we can make it, and let's slowly start making this be smaller and smaller and smaller. Okay, I see little bits of the green getting smaller, but even right here, I don't see any change as I wiggle delta. Now, why is that? Why is there no change right here? The reason why there's no change is because right here, this function, this part of the function is decreasing, and this part of the function is decreasing. So as I decrease delta, I'm actually not seeing any change. Eventually, it's going to be getting smaller, and then it sort of kind of stagnates out again, and eventually getting smaller. So it doesn't always get smaller, but does it ever get larger? No, it never did get larger. So sometimes it stayed the same, but it's never going to get larger. And lastly, does the green area always shrink down to a single point? So let's make it be smaller and smaller and smaller. So the smallest that this applet can go is 0.001. Can it be smaller than 0.001? You betcha. Just not on this applet. That's the limit of this applet. But really, delta just gets smaller and smaller and smaller and smaller and smaller. So here I get a single dot. But where do you think we should move this so that way we don't get a single dot? Well, one thing to try is just to drag around C right here. So drag around C, do I get single dot? Yep, single dot. Yep, single dot. Wait, I just got 2 dots. Now why is that? Let me make delta a little bit bigger. As I make this smaller and smaller and smaller, the intervals are either staying the same or getting smaller. And eventually, as this limit gets smaller and smaller and smaller, it doesn't go to the same point. Now, if I plug in C, it says that C is 1.36. C is 1.36. The reason for this is the floor function, this value right here would have like a closed dot, and the value right here would have an open dot. As I make delta smaller, watch from the left side. It's never going to leave that lower part of the function. Just below, just barely smaller than 1, the function is on this lower part of the graph. It's not going to jump up there until it is at 1. And so this limit is always going to be this little bitty piece. It's just below 1. So the limit actually does not exist because it equals 2 different values. So the limit doesn't exist at 1. I can plug in a value at C, but the limit does not exist. So no, it does not always shrink down to a single point. All right, now let's graph this one. You don't have to type this in. You can just go to examples and pick 5. So what is f of 1? Your C should already be at 1, and we can see that, well, f of C is question mark. That's weird. Let's move C a little bit. Okay, well, it is working. It is calculating an f of C, but what's happening at 1? If you remember from your algebra classes, there's a hole. The technical name for this, it's a removable point of discontinuity. The reason for that is this x minus 1 reduces to 1 with the x minus 1 below it. So there's a hole here. If you try to plug in 1 to calculate this, you actually get an undefined. It doesn't work. If I plug in 1 right here, you get a divide by 0 error, but on top of that, it also then reduces to 1. So that point of discontinuity got removed, and that's where this hole got created. But the good news is we have the limit. As it gets smaller and smaller and smaller, it's approaching the limit if it exists. And in this case, the limit does exist because it is approaching that single point, and it's approaching that single point right here. This one dot, this one value that's on that y-axis. And that's actually 0.8414. And you can calculate that by literally removing the hole. You can remove this x minus 1 from here when it reduces away. Just plug in sine of 1, that 1 being a radian, and you get 0.8414, and that, of course, keeps going. So hopefully this has helped you understand limits a little bit more. Feel free to look at some of the other examples and play around with this applet some more to help your understanding of the limit.